machine learning workshop presented by Nexus Club. In this workshop, we will be diving deep into the ML world, from understanding the core basics to exploring real-world algorithms like linear regression, KNN, and decision trees, and more. Whether you are a beginner or just brushing up, this workshop will surely help you build your interest in machine learning and AI systems. So we have three speakers. Our first speaker is Sekkappan, tech lead at Nexus. He is an intern at IIT Hyderabad and a driven contributor across AI-based clubs. His passion for ML is backed by deep knowledge and energy. Next up, we have Naman Kumar Singh, AIML lead at Binary Club and a team member at Nexus, a true machine learning and deep learning enthusiast with a sharp eye for intelligent systems. And finally, we have Shubhansh Nigam, technical member at Data Science Club, known for his consistent work in ML and practice problem solving skills. Also, we are grateful to have faculty of Dr. Sekhar Satyanarayan, who is an associate professor at VIT University with a specialized in signal processing, computer vision, deep learning, and data analytics. He earned his PhD and MS degrees in signal processing from Nanyang Technological University, Singapore, in 2017 and 2011 respectively. Following his BE in Electronics and Communication Engineering from Anna University, Chennai. He also served as a research fellow at NTU from April 2017 to April 2018. Now, I would like to request to speakers to take over and begin the session. Thank you.
Thank you, Udit, for that nice introduction. So, I'll be beginning with our workshop. Just let me present my screen. Hopefully my screen is visible. Okay, I'll figure out how to make it full screen later on. Right now, I'm here to tell you that this workshop is basically going to be a gentle introduction into what what ML is and how you can dive deeper into it if you are interested in it. We'll be using a lot of terminologies during the workshop, and I'm here to brief you about them before you see them later in the workshop and panic about them, because ML has a lot of terminologies. So I'll be beginning by what machine learning really is. So machine learning is a science of making computers learn about patterns hidden inside data and using those patterns to predict future data points. So what that could mean is, let's say I have a housing data set, in which I have the number of rooms inside a house, the size of the house, and I could use that information to predict what the price of the house could be. Or let's say for another example, I take an advertising company. I take its how much budget it allocates for sales in for marketing in TV advertisements, in radios, in newspapers, and see how that correlates to the increase in sales. All of these are patterns that are hidden inside the dataset, and machine learning is just trying to find those patterns. So a lot of terms that we'll be using inside the workshop are supervised learning, unsupervised learning, and reinforcement learning, which are the three major concepts of machine learning. They are quite simple things, to be honest. Supervised learning is basically just giving the model a target and making it predict that target using the features that we give it. What are features, you might ask? Features are the qualities of the dataset that you get. As in the housing dataset, you get the size of the house or the number of rooms of the house. Those are the features, the descriptors, or you can call them the predictors. We have a lot of terms for them. If your target value is a numerical value, if we take the housing dataset again, that numerical value is price of the house. We call that type of learning a regression task. So we're trying to predict a value instead of a number or a label or a class. If it is a label or a class, it is a classification task. Inside classification, what we do is try to classify what the target is saying into different classes. Classes could be, let's say we have medical related data set. We get a size of a tumor, we get information related to a tumor, and we can classify that information into whether that tissue is actually a tumor or not. That is, the output is either a 0, that is not a tumor, or 1, which is a tumor. In regression, it's a numerical value. In classification, it's a class. In unsupervised learning, the major difference is we don't get a target value. We do not know what we have to predict. So what the model actually tries to do is cluster, find patterns to clump up data points together according to some of its features being close to each other or being related to each other. There are two major types of unsupervised learning, mainly clustering or association. What clustering does is mainly to classify stuff close to each other. So inside a clustering algorithm, that we know that bread and butter are kind of related to each other if our dataset is a grocery list dataset. We have a list of all the groceries. We have some values, or let's say we have sales values related to those groceries, and we can cluster them together. We know that a lot of people who buy bread will also buy butter. Association is trying to find features, which is trying to correlate each data point with its predictors to other data points with similar predictors. So coming on to reinforcement learning, which is beyond the scope of today's workshop, but we'll see what it is briefly, because it comes under the three main types of learning under machine learning. So reinforcement learning is treating your model like a child, I would say, to put it in simple terms. And whenever it does a correct prediction, we give it a treat. We give it a candy. Whenever it gives a wrong prediction, its performance is bad, we give it some punishment. So we do this over a loop. So over time, the model learns that whenever it does a good prediction, it does this thing better, it gets a reward, and it does this bad thing, so it gets a punishment. So not to do the bad thing, always do the good thing. That's how we train a lot of models that we use in the real world. And it is a major form of learning which is part of machine learning. What we'll be seeing today majorly is how Uday described it, which is linear regression, k nearest neighbors, decision trees, and how to choose different models. In linear regression, we'll be seeing how linear regression majorly works on, like, from a top view, how it's implemented, how it performs, how k nearest neighbors works, and also why do we need k nearest neighbors, why do we need different models, what's the use. We try to understand that, decode that in this workshop, and then how decision trees work, and why why do they how do they make those decisions, or how do those come to which decisions are best to make and which ones are not, and how to choose among those different models is what we'll be going through in this workshop. This is just the introduction, so I'll be calling Naman to start with the linear regression part.
We have obtained clean data which can be fed to the machine learning systems to train it. So starting with the terms that are going to be used throughout the discussion. So first we'll look at what is data and the matrix representation of data. So suppose we have, a data set. So these rows will represent, usually in, machine learning notations and everywhere you will see, this is how they are represented. So you have n data samples. So all rows represent each data sample, and you will have m features for every, like you may have m features for each data sample. So it can be everything. So as I said, for example, like if we're trying to predict house prices, based upon like where the house is, so the features can be like anything, like number of rooms it has, number of bedrooms, how far is it away from a particular thing, what is its locality, is it in a rural setting or urban or something like that. So all these are like predictors, as Shubhansh said. They contribute to the, in a way, they contribute to the price of the house. So each sample is mapped to its particular value, and which can be represented in the target vector. So that's it. The input is a matrix, usually denoted by capital X, and the target vector Y. And the prediction being made by a model gives us Y hat. So, that is what we are going to use, like the differences between what the actual value is and what our predicted value is, to make our model a little better. So we feed our model along with the target variable, train it to predict better. And now let's look at some of the data preprocessing terms. So usually when you have a data set, you there's a standard practice to divide it into train set, validation set, and test set. So why is that so? Like validation set, mostly Sekkappan will be covering this part as to how model selection is done. And training set is a standard practice to keep some data aside. Like you're trying to keep some of the data aside. Like your model shouldn't have looked at it like throughout the course of training, so that it doesn't overfit. The thing is, like, even without the term overfit, if I would like to explain it to you, like what overfitting is, it's like it performs well on the training set, but when you give it the test set, you give it some data point outside the training set, it fails to perform. It performs poorly. So analogy that I can draw is like mugging up answers and actually learning the concept, or maybe like a mathematical formula, it, but you don't know how to use it. That's the difference between the model performing good on the training set versus the actual test set. So that's one thing. So we have finished with what the terms that we are going to use. Now moving on to the handling of missing and categorical data. So there are for like two ways to handle missing data. First is dropping the entire rows or columns. Like this is a no-brainer kind of thing. Like that's how I avoid most of the problems in my life. So next on imputation. Data imputation is the process of replacing missing values in a data set with substituted values so that the data can be used for analysis or modeling. So in this case, like the other data points or the variables are used to kind of fill in the void. So all these data sets here that you can see in dark green are used to fill in the missing value. That is, we impute it with like the common imputation techniques are replacing it with mean or median or mode values of the other data points that are present in the data set, and that's how um, fill in the or missing values, and you have a data set ready. Now moving on to handling categorical data. But first of all, what is actually a categorical data? So categorical data features contain labels or names, not numerical values. So as I said, like for example, shirt sizes may be represented as small, medium, or large. So it's not like we have being a numeric. We can have numeric values for them as well, but it's a general notation of using small, medium, or large sizes for shirt sizes. It's just an example. Like you can think of more such examples as well. So a linear regression requires numerical input. That's why you have to convert these categories to numbers. Let's look at how we do that. So there are two ways that I'm going to discuss. One is ordinal encoding, and the other one is one-hot encoding. So ordinal encoding is used when the categories have a meaningful order. Like you're trying to give it a number, but like how do we decide like what number to give it? So suppose I'll take example of education levels. So suppose you're trying to predict what salary a person will draw, and it says education level is one of the features. So it's in order, right? The high school is the most primary level you can see in this list. Then we move on to bachelor's, master's, and PhD. And so it assigns increasing integers to the ordered categories. That's how simple it is. So it is mostly used for ordered data. But one hot encoding is not like that. Suppose you have some kind of categories that they don't have an inherent order associated to them. So you simply uh, uh, convert each category into separate binary column. Like it will take up values of zeros and ones itself. Like if this data point represents a t-shirt, like data point P1 represents a t-shirt of large size, like one will be marked in the large column. That's it. So that's how we take care of the categorical data in machine learning tasks. Now moving on to like what linear regression actually is. So as Shubhansh discussed before this, it's a supervised machine learning algorithm, and what it does is it predicts a continuous output y from input features x. Uh, and the simple way to look at it is a mathematical equation, a line equation, y equals to mx plus c. It's as simple as that. So what we have to do is find the m and c in this equation. That's what. So instead of just m and c, we may have more such parameters for this. It's for multivariable equations, and that's what. And in our notebook implementation, we'll be looking at the housing prices data set and try to make a machine like a linear regression model ourselves. And so yeah, that's how a typical linear regression line fits onto data points. um, yeah, but the question is like, how does it learn? So one more thing, like we can have any line, right? Instead of this green line over here, we can have any sort of line, and like to be honest, it's a model, like, but it doesn't give you good predictions, right? So our task is to minimize the errors that happens in the actual predicted value and in the predicted value and the actual value. So that's what we are trying to minimize over here, and that's what we do in a typical machine learning flow. That is, we start off by initializing parameters, that is the weights and biases, with some random value. So this equation generates some prediction which is certainly not good, right? And like, how do we know that? We use a cost function to determine that, and eventually, our goal is to minimize this cost function, which is done by various methods, one of which is gradient descent. So it is one of the optimization algorithms that we use, and in our deep learning workshop, we'll be covering this in detail as to how this works. For now, I'll just move on to the implementation. Right. So on to the Jupyter notebook now. I'll be sharing the link in the chat. I hope there is a chat, accessible to everyone.
Yeah, I'll make it.
Okay. Yeah, so anyways, I'll be showing you the implementation, like running the cells one by one, explaining what each code snippet does, like give you a general overview, because we need to wind up the session by 12. And you can just, I have uploaded the link over here. You can run the notebook anytime you feel like. So moving on to the notebook implementation. Yeah. So what we are trying to do is, given the data of houses in various districts, what we are trying to do is predict the house prices. Now, why is it important? And first of all, Sir made a good point as to how to decide what type of machine learning model, should we use. So you should always ask yourself questions regarding, the problem statement. So is it going to be a supervised learning task or a unsupervised learning task? So in this case, of course, we're trying to make a prediction. We have data set available and labels available, and we are trying to train the model on that. So of course, it's a supervised learning task, and a few other things as online learning and batch learning. We'll discuss that in the next few sessions. And yeah, so like these questions can help you, better decide what kind of model are you going to use. So coming on to our implementation of the code, like this is an general imports that we have. Now importing NumPy, Pandas, Matplotlib, the scikit-learn library. That's all it is doing. And then moving on to the data loading, it's a snippet I got that directly pasted it. Get the data directly from the GitHub repo that they had, and yeah, data loaded successfully. So as you can see, it has 20,640 data samples, each having 10 features. Now let's have a look at what those 10 features are, right? So each data sample has these features: the longitude and latitude, that is where the house is geographically present, then the housing median age, the total rooms, bedrooms, population, households, median income, median house value, and ocean proximity. Now I'd like to focus your attention onto these two: median housing value and ocean proximity. So median house value is the label that we are looking at. Like this is the thing that we are trying to predict. Next up, we have ocean proximity. So this is the categorical data that we have to take care of. Again, running the .info method, we get the details about how many null values do we have and the data type it is. So everything is float except for the last one, that is ocean proximity. And on closer look, like the total bedrooms features, like it has few data points missing over here. As you can see, everything is complete, 20,640 data samples. But some points are missing from the total bedrooms part. So we have to impute that. So I'll take care of that as well. And as for the ocean proximity, we look at what types of categories are there. So less than 1 hour from ocean, inland, near ocean, near bay, island, something like that. And data description, as you can see, like it gives you mean, standard deviation, min value, max value, and all sorts of things. So you can have a look at that as well. Now I'll visualize the data, like plotting histograms to have a better understanding of what it is doing. So as you can look at it, like some of these kind of fit into the Gaussian distribution, some not, some are very skewed. So we take care of that as well through various type of transformations, which I'll show over here, which haven't been discussed before. But like when you have skewed data sets, taking the log value or something like that, that helps bring it to a bell-shaped curve that machine learning models work better with it. Now we prepare the target variable. It's just the median house value, that's it. And now coming on to stratified sampling setup. So in a population, like suppose you're trying to predict something, and the population you have, you're looking at two major groups of people, male and female, and say your sampling has only 30% of females and 70% of males, which is not a true representation of the population, true representation of the population. So every time you have some data, it's important to have the proportion the same in both the test set and the training set, so that you have a proper representation of them throughout. So that's what we are doing over here. And you can see I have created categories over here. That's what I'm doing. Categories by income. So, yeah, over here. So distribution of income categories. And as you can see, the number of districts are being plotted against income category. So how many people have taken houses from each income category. Now we perform the train test split. For that, I'm just using the sklearn library, and from that I'm importing train test split to do that for me directly. And I make sure it is stratified by the income categories that I created. That's all. So we have the training set size as 16,512. It's usually 80-20 ratio. And now moving on to preparing the data set. So for that, like the data that we got, it is a data frame is there, and we have the median house value from it. Like that's the label. So we need to drop that from the actual data set and use that for the training set itself. And oh, okay, I'll send the Jupyter notebook link again. Yeah. Yeah. So preparing the training data set. So we drop the median house value from the actual data frame and create it as a separate vector over here. That's what we are doing. As you can see, shape, it's now left with 9 features instead of 10. That's it. There's 9 columns instead of 10. Now in geographic data visualization, we won't be working with this because it will get complicated. I'll just show you how the population density is throughout the state of California. That's it. And now one mathematical statistical tool that we're referring to is the correlation analysis that we're going to perform in the data set. So median housing price against all the various features that we have. Cool. So what will that signify? That is how strongly the median housing value changes with every other feature present in the data set. That's it. So we'll skip this one because this is the same thing. Of course, it will have the value 1. So it lies between -1 to 1. And the median income seems to be a very good feature. Like it is strongly correlated with the median housing value. And now moving on to we'll create some new features. So one more thing, as humans, we have basic intuition about various things. So as you can see, it has features of total rooms and total bedrooms and say population in a particular district. So I don't feel like that they are good measures of they're not good features, to be honest, because what will I do with total rooms present in a district? Like total number of rooms present per household would be a better feature in my opinion. So I'll just experiment with it. And here's what we're doing with feature engineering and creating new features. So now I've created rooms per house, which is total rooms divided by total number of households. And as for the housing, like bedrooms ratio, we have total number of bedrooms divided by total number of rooms. And for people per house, we have population divided by household. That's what we're doing. And we'll perform the correlation analysis again on the data set. So as you can see, now rooms per house is, better correlated with the total number of rooms and other such things as well. So that's what. And now we'll create a pre-processing pipeline setup. So I'll just give you a quick overview of what it is doing. Like in the column, like the columns transformers that we're using, and for the row transformer that we are using, the stuff and the data set. And for the columns, we are just trying to impute the values. That's what we are doing in these few code cells. So pre-processing pipeline created, and now creating a linear regression model is like very easy, like using scikit-learn. All you have to do is import linear regression from the scikit-learn library and simply create an instance of the make pipeline that we had over here, in which everything will be pre-processed first, and then we'll apply linear regression on the data set. And that's it. Our model has been trained, and now we can perform cross validation. I won't be taking care of this part. Sekkappan will give you a better overview of what it is doing. And then we have like the training set performance as to how is it performing on the training set. So R2 score is 0.65, which is not good, but we did not play around with the data set much. So it's average performing, but it's like you got an overview of how to train a linear regression model. Same we are doing for the test evaluation. Yeah, again we have our 2 score of 0.61, and mean absolute error, it's like way off, like it's not good at all. But yeah, playing around with features, and also this gives us a idea as to linear regression might not be a very good model for this particular task. And we can go with some other models using random forest or decision trees for this task. I will just visualize as to how the line has fitted over here. So yeah, you can see like this is the line that we're fitting in this thing. So that's what. And yeah, that's all from my side. And this is a complete implementation of the code. And this is how you can create your own linear regression model from this is not from scratch implementation. We have used scikit-learn library, but in the upcoming session we'll be showing that from scratch as to how gradient descent works, how a cost function, like how do we choose a cost function, how do we use gradient descent for the task of uh, uh, training the model and optimizing it. So yeah, that's all from my side. Now Shubhansh will be explaining k nearest neighbors model to you guys. Over to Shubhansh.
Thank you, Naman. You have made my job a lot easier by explaining a lot of things that I was going to. But some things I'll have to take over. Yeah, so hopefully my screen is shared. Yeah, so I'll be taking over for explaining what k nearest neighbors algorithm is, how it works, why do we need another algorithm. That's what I'll be focusing on in the beginning, because as sir before we started, as sir told us there are a lot of machine learning algorithms out there, thousands if we take in the variants as well. So why do we choose different models for different tasks, and why do we need those models is something that you need to answer before you know if you before you know how to go for a lot of different models. There's a quotation that says, if the only tool in your shed is a hammer, you'll be treating everything as a nail. So if you only know linear regression, you'll try to treat every data set as a linear data set and try to fit a linear regression model inside that. But even if you know a lot of models, you might not know what the drawbacks of linear regression are and still not utilize all the models that you have in your arsenal properly. So I'll be talking a bit about that at first. So at first we come into what makes a model a good model. And to kind of explain that, I'll have to explain what bias and variance is, and uh, and go into what bias variance trade-off is. So what bias is something is it comes out of assumptions that a model makes. Every model makes certain assumptions, like the linear regression, which you have just learned about. It's in the name itself. The assumption is that the final function is a linear combination of the predictors that we have. So the outcome will always be linear is our starting assumption. That's our bias. Biases can be different according to different models. We'll be seeing what the bias for KNNs are, and every model has its own bias. Biases are not a bad thing to have. What is variance is it is something completely different. Variance is how much the prediction of a model changes by if by the amount you change the data points inside that you feed the model. So let's say if you change just a single data point, if you have a whole data set consistent of 100 data points, and if you just change a single data point, uh, let's say if you have had a value of 2 rooms in the housing data set, 2 rooms and 100 square feet of house, you change that to 3. If the prediction of the model changes very drastically, that would mean that the variance of the model is very high. That is not a very good thing, because in reality, the predictions should be kind of constant. They shouldn't just depend on a single data point. That would seem like your model is not confident. As soon as a single data point changes, its complete assumptions about the whole data set are thrown away and a new set of assumptions come in, which shows that your model wasn't confident in the first place. So that's not a very good thing if your variance is high. Variance low means even if you change a lot of data points inside your model, the predictions are still around the same, which is a good thing. It shows that your model is kind of confident. So, uh, as you can see in the image on the right here, high bias would show that there's some inherent assumption that the model is making which is wrong, which is causing an error which can't be reduced. If if the dataset is a parabolic dataset, that is all the data points inside the dataset form a parabola, and if you try to fit a linear model, there are some things like there will be some error that you won't be able to reduce no matter how much you train the linear model. In the high variance part, you can see uh, this is high variance and low bias. So even though we can get high accuracy in this, which is something near to the center, we aren't getting that all the times, because every time we change a certain data point or some data points, the model is changing its predictions, and which is leading to our predictions getting all over the place, which is not a good thing. These two lead to, if you have both high variance and high bias, that is what the figure in the bottom right would look like. But in machine learning and in general, if you have a low bias, if you have a low variance, that's a good thing. That's the perfect model that you have. Now, in machine learning, we have this term which is bias variance trade-off. That is, whenever your bias of your model decreases, your variance will go up. Always. This is kind of a law that is always the case, and you have to find the balance to find to get the correct predictions. If I talk about what the side effects of high bias are, what the side effects of low bias but high variance are, which I have, you can see in this figure on the right, but it's mainly to do with how, if you have a lower bias or a high variance, your model will also get less interpretable. So, what that means is, if your variance is very high, your uh, your model is interacting with each data point and trying to predict all the values of that data point. We'll be seeing what this looks like graphically in the next few slides. I'll just give you an overview now. So it will try to interact with each data point, and that will make a lot of curves inside the final prediction, which is not a very readable or a understandable thing. The equation will be very complex. If your model has a high bias, let's say in a linear regression, which is a very high bias towards a linear model, linear regression is very interpretable, because we get all the predictors combination equal to the target value. We get an equation which has the combination of all predictors multiplied by some coefficients, and that is equal to what the target is equal to. So we'll see how that looks like inside a data set. So let's say in this you try to fit a linear model. What would happen? Maybe your model will go like this. It'll try to reduce some of its error. Maybe it'll go a bit like this, a straight line. Of course, I can't draw a straight line on my mouse. Sorry about that. And at the end, I feel like it could settle for something like this. But as we can see, it isn't capturing the essence of the dataset, which is a parabolic data, which is showing a parabola clearly, and this shows a high bias towards linearity in linear regression, of course, because of its name. Let's say we have a very powerful model now. We have something that can fit each and every single data point in this dataset perfectly. That is, all the available data points that it can see, it tries to fit a curve that captures all of them perfectly. So its training accuracy would be 100%. It will be 100% accurate on all the data points that it can see. So it will look something like this. Yeah, so as you can see, it will turn out to be very squiggly, very curvy, because it's trying to capture a lot of information in which it doesn't really need to. It doesn't always need to be 100% accurate on training dataset, and actually being 100% accurate on just the training dataset is called overfitting. We'll be seeing this term more often in our upcoming workshop. But what overfitting really means is that the model is learning the data points that are available to it by heart. So it's just mugging up the answers on the answers that it can see, which doesn't really generalize to like actual knowledge about the data set. it is very not confident about what the dataset is actually trying to say. What the dataset is actually trying to say is a model like this. This is actually, I plotted this parabola and added some Gaussian noise to it myself. So this parabola was actually y is equal to x square with some noise added to it. So the true equation behind this model was actually a parabola, which if a model could have predicted a parabola like shown in the red here, it would have been a perfect prediction because that has the right number of the right amount of bias and the right amount of variance in it. So that's all for bias versus variance trade-off for now. All you should take away from this previous thing is that the final model that you choose should have a low bias and a low variance. You have to somehow find a right balance so that neither of them are too high. And of course, it's a trade-off. Whenever you go for a lower variance, your bias has to go higher. So
Shubham, it's a good explanation, very nicely explained. Yes, but one thing to note for the audience is this variance is different from the statistical variance. That the term, right? Not the square of standard deviation.
yes, sir.
Yes. For people who are new, right? Well, I also in the beginning was confusing it with that statistics variance. This is totally different. This is not that variance. Yes, nice.
Yes, sir. I should have mentioned actually. This is
I also. People should not easily, right? Because in every course, right, we are dealing that term. So this is not that square of standard deviation variance. Yes, right.
Yes, sir.
Okay, good, nicely explained. Yes.
Okay, thank you, sir. I'll be continuing.
Yeah, you can continue. Yes.
So, coming back to my main topic, why learn about KNNs? Why talk about them? Why are they useful? In fact, so we learned about linear regressions before this. Just now you have seen that. So I'll be comparing KNNs with linear regressions, which is fresh in your memory. So you'll kind of understand what the advantages of KNNs could be. Linear regression at its core is a parametric model. That is, it relies on its predictors to form an equation to form some sort of answer to what its prediction will be. So the equation that it finds, which has the least error in it, is the combination of its coefficients with its predictor values to find the target. In KNNs, they are non-parametric, so the combinations of the predictors doesn't actually matter. The assumptions that KNNs make are that the points that are close together have similar values or have the same values. So in real life, an example would be like our parents tell us that your friend group defines who you are as a defines what your personality would be like. So they tell that to tell us to make good friends. That's the kind of logic that KNNs are using. That the points which are situated close to each other will have similar values, and a core key difference between linear regression and KNNs are that in KNNs you can very easily manipulate the bias and the variance of the model. We'll be seeing that ahead. I'll be showing that to you graphically. So at its core, what the KNNs are doing is you have a target value, you have a value that you want to predict what class it belongs to, or even what value it can attain. KNNs can be used both for regression and for classification, though they're mostly used for classification because they show much more promise when it comes to classification, much lesser error included there. So you take a arbitrary k, you choose your own k value, k is the number of closest points that you'll be finding. So let's say 5. For now, you'll be finding 5 points that are closest to the value you want to predict the response for, the vibe for, and you take the average or the vote for those fives. So if you are training for a regression task, you're trying to find the value of what the y will be. You take the average of those 5 points. In a housing data set, that will be the average of the price of those 5 closer houses. You take the average of that. That is the price of this house that you're trying to predict the value for. If it's a classification task, if you're trying to classify things into zeros or ones, or tumors or not tumors in case of a medical data set, or like if you have a specific problem related to that, if you have more number of votes for ones or tumors than the number of votes for zeros or not tumors, you classify your point as a tumor or one in mathematical terms. That's the core working of KNNs. What that will actually look like. So if let's say our k was equal to 1, this red point is the target that we want to predict what class it will belong to. All of these points are different classes. So red is a different class, and this blue is a different class, green is a different class, purple is a different class, and yellow is a different class. So if our k was equal to 1, we'll try to find the closest point to it, this one, and we'll predict this target value to be part of the green class. If our k is equal to 2, we'll take another value. Still green is in the majority. If k is equal to 3, another green value will be taken. But after that, it will start taking values from red, blue. It will go all over the place, try to search for the closest points and see what kind of response that we get from averaging those values. It can lead to some unique interactions. We'll be seeing that in this graph. So hopefully you can see this. So in this we have 3 different classes, which is black, which is class 1, the red points, which is class 2, and the yellow points, which is class 3. These points are all plotted, and the shades in this in the rest 3 of the graphs denote what points. So inside the orange shade, each point is classified under class 1, which is the black points. So all these points inside the orange part denote class 1. Inside the yellow part, they denote class 2. Inside the dark blue part, they denote class 3. I think I said yellow for this. This is light blue, which denote class 2. You can see an interaction going on in there. Since k is equal to 2, which is very small, so when k is a small number, it shows that our model has a high variance. Why does it have a high variance? Because every time you change one of the data points inside the model that you feed to the model, the predictions will change. Because if let's say k is equal to 1, it relies heavily on what each predictor is saying, what each data point is situated, because as soon as that data point isn't there, it has to look for a new one. The responses will change immediately as soon as you remove a single data point. So that means it is a very high variance but low bias because it is a very normal assumption to make that if 2 points are very close to each other, they're almost the same, their values will also be the same. That's a good assumption. That's why it is a low bias but a high variance thing. And that is not always a very good thing. As we can see over here, it has this weird interaction over here because the number of red points are low in number over this region, but they're sparsely placed inside some of the yellow points. So a lot of the regions which are getting placed, they're getting marked as blues, light blue or class 2's region, is doesn't really have a lot of red points in it. It's just a couple of red points changing the values over there, which shows it has a high variance. This part is what I'm talking about specifically. Now you'll see, if we increase the number of k is the number of uh, k is the values that we're taking. If we increase the k, we can see that the graph smooths off. It becomes very smooth. It shows that our variance has dropped a lot, and our bias resultantly had to go up, because that is how the trade-off works. The variance is low because it doesn't just change according to what this one point is saying over here, or this one point is saying over here, that those couple of points which are inside the yellow's territory don't change the predictions over there. The majority of the points over there are still yellow, so that's why they get marked off as class 3, which is, I would say, the correct prediction over there. But if we increase k to a very large number, which we can see in the d model, k is equal to 100. So what happens over this deep blue region is the model is counting every single data point over there, since k is a very large number, and it completes almost all of the points that are situated in this region gets covered up. And we can see that the number of yellow points is much higher than the number of red points in that region. So just because the number of yellow points is higher, all this complete region is marked off as class 3, because it comes down to a vote, and yellow has more number of votes in that whole region. Which means that our model has low variance but a high bias. Now, which is again a bad thing. We started increasing our k, our model got a bit better, we dropped our variance, our bias increased a bit, but our overall accuracy improved. We kept on increasing our k to a certain degree, and our accuracy went down again, which was because of the high variance, the high bias that we now have. So now that we have seen how it works, what it's doing, I'll tell you about the drawbacks of KNNs. It's not a perfect solution for everything, as you might have noticed. KNNs can be better or worse than linear regression, depending on what your end goal is. Linear regression gives you a really interpretable model. Let's say you're working for an advertising company, and you have to figure out how much money you have to put into advertising on a TV ad, or a radio ad, or a newspaper ad. If you train a linear regression model, what you'll notice that is you'll get some coefficients of the trained model, and how high that coefficient is means how much that value increases your target prediction. That target prediction being how much your sales are increasing. So let's say your coefficient for TV ads is high, so that means the more money you put into TV ads, the better your sales will be increasing, which we don't really see in KNNs. We don't have any interactions with the parameters themselves, so we won't know what TV sales or radio, not sales, sorry, what TV ads or radio ads or newspaper ads would be better for increasing your sales, which can be seen in the linear regression part. If your data set has a large number of features, if you have a very large number of features or descriptors, your whole space that you're covering, space being the number of dimensions that your data set is covering, becomes a bit sparse. It becomes hard for the KNN model to find the correct neighbors to it, and that's why we call it the curse of dimensionality, because it becomes hard for the model. Not just KNN, but most of the models get affected by uh, a large number of features in some way, but KNN especially, they get affected by not being able to predict properly, because some of the features might not be actually in any way related to what the predictions that you have to make, and those actually make your data set kind of useless to work with if you have those inside your data set. And thirdly, lastly, if the true form of your dataset is linear, like your bias is correct for the linear model, your bias being that the data is distributed in a linear format. If your bias is correct, that the data is actually linearly distributed, you'll of course get a better linear regression model than a KNN model, because your assumption that you started the linear regression model with was found to be correct. KNNs have a worse inference time. There's two types of times or related with machine learning models, that is training time and inference time. Training time is how long a model takes to train. uh, all the models have, not all the models, but a lot of models have their own set of weights parameters that need to be tuned and trained before you can use the final model. That whole training process takes up a lot of time in some models, not that much time in other models. That whole time is called training time, and inference time is how much time each model takes to do its prediction, to just take the final model that your algorithm provided and use that model to predict the values that you have. That is called inference time. KNNs have a very good training time because their training time is zero. You don't need any training for a KNN model. But your inference time suffers because of it. It is also a trade-off that you can say. It suffers because every time you want to make a prediction of a target, you have to find the distance of that target from each of the values that are present inside your dataset, and then find the k points which are closest, which have the least distance to your target that you want to predict of. And once you find those k distances which are the least, then you take the average, and that increases our inference time, which is not really a good thing, but it makes up for the low training time makes up for it. What situations would you be using the k nearest neighbors algorithm in is, if let's say if your dataset doesn't have a lot of noise, does not actually have a lot of redundant predictors being predictors that aren't contributing to the target, that are in no way useful. If I were to give an example, like I could say how many, if you want to predict the number of shark attacks in a certain beach, and one of the predictors you have is the number of ice creams sold in that beach, it is in no way related to what you have to predict, but you might notice that if the number of ice creams sold in that beach go up, the shark attacks might go up as well, because they are in a very loosely correlated situation. That is, if there were more people on the beach, that means number of ice creams were sold higher, and that means the shark attacks have a higher chance. But ice creams are in no way related to shark attacks. That's what redundant predictors would mean. If you don't have those, you have a clean data set, you can go with KNNs. You can manipulate their bias and variance according to your needs, and you'll get a very simple and a very high accuracy model very fast. You can also explain KNNs very easily. Why is it performing very good? Because uh, the data points that are close to it have correct values associated with them. That's why it's performing as it is. It is KNN is like one of the simplest algorithms to explain uh, to explain what it's actually doing. And KNNs actually work very well when their decision boundaries are non-linear. So in linear regression, we can see everything is linear. We can't do anything about curves or anything present inside the dataset, but KNNs can work with non-linear stuff. You can use them when it's needed. When you have a dataset which is non-linear, you can use KNNs for that as well. So I'll be going for the implementation, show you what KNNs implemented looks like. So yeah, you can see this. I'll be going over this quickly because Naman has done a lot of my job in explaining what the code is actually doing. So I'll be running this and trying to explain what the code is doing side by side. We have to wrap this up really quickly as well. So first of all, I'll try to simply make a simple plot of three data points in one class and another 3 data points in another class, and use a new point and try to show you how distances are calculated. So these blue points represent one class, these red points represent another class, this green point is target value, a new point that which we want to predict which class it actually belongs to. And the distance that we calculate over here is called Euclidean distance. Euclidean distance is a big term for basically under root x square plus y square. X square being the distance, the difference in x coordinates between the selected point and the target point, and y square being the y being the difference between the y coordinate difference between the y coordinates of the selected point and the target point. Euclidean distance is and there are three types of distances: Euclidean, Manhattan, and Shebeshov. It's a Russian name. It's a bit hard to pronounce for me. So as we can see here, two of the closest points were belonging to the blue class. So the final prediction of this green point will be belonging to the class 0, which is the blue class. Why do we have three different types of distances is what I'm going to talk about in this this whole piece of code. So what it's trying to show you is plot a contour graph of what distances look like for each point in the xy axis for each type of distance. First off will be the Euclidean distance, which is under root x1 minus x2 square plus y1 minus y2 square, which is the general form of distance that we use in most cases. Why is this hard to why do we not use Euclidean distance everywhere? Is because it's hard to compute. You have to take the square of numbers and then take the square root of their sum, which is a bit harder to compute. it increases the inference time. We have seen in the drawbacks that one of the key drawbacks of this is higher inference times. So to reduce that, we use either Manhattan distance or Chebyshev distance. What Manhattan distance is, in fact, is nothing but just the sum of the difference between the x-axis and the difference between the y coordinates. So sum of difference in x coordinates and sum of difference in y coordinates. That's what Manhattan distance is. We can see how it plots like in the contour graph. So I should give a basic understanding of what this contour graph is saying as well. Each of the white points that you see in here represent the same d value, d being the distance. Each of these white lines, all the points in this white line have the same distance from the center, from the star. I think that will be enough to help you understand what the distances would look like. In the Chebyshev distance, the distance is calculated just, which is max of the difference in the x coordinates and the difference in y coordinates of the target and your predictor that you're searching up against. So it is much easier to compute either the Chebyshev distance or the Manhattan distance when compared to the Euclidean distance, which is something that we use to make KNNs more efficient. Of course, that changes the distance a bit, but that is not a very huge change. So now we'll go straight ahead, see how KNNs are working in a graphical way. So here I am taking a set of 100 random points. This make classification function gives you a set of x and y values according to the specifications that you give it. N features I am giving it 2, so it will have 2 features. Number of redundant features I'm giving it 0, so nothing, all the features are useful for the entire classification. So n informative means 2 informative features, that is, yes, we have 2 features and both of them are informative features. Number of clusters per class, that is what cluster is a class based around. If there can be multiple regions that a class is located at, that is called a cluster, and each class is located around one cluster. We'll be seeing that in the graph. And random state is just a seed number that to generate the point randomly. This test point is any point. We'll be changing this later. I'll be showing it to you. But test point is any point that we want to make the prediction for. I'm plotting all this over here. And then over here, what I'm trying to do is test out 2k values for 3 and 7. I try to find the distance. I'm still using the Euclidean distance over here, you can see. I'm trying to find the distance of all the points from our target value, and then I'm sorting the distances and finding the k nearest ones. This is what this piece of code is doing. I'm trying to find the k nearest pieces and then use those pieces to predict what my target will look like. Again, that with k is equal to 7, and this is what our graph looks like. This is one cluster which is class 1. This is another cluster of class 0. We'll call it red and blue. So here is a heat map of the distance, what they'll actually look like. The purple means the lowest distance, the yellow means the highest distance. So the predictor gets allocated to the number of it sees what predictors are close to it and it takes that class. So in this k is equal to 3, all the 3 predictors are of class 0, class red. So it takes on red as its own classification. In here, one of the predictors is class blue, but still the majority is class red, so it still remains class red. Now we'll be seeing what we have a different data set now. We have made changes to it. We'll be seeing what increasing the number of k does to our predictions. So over here, when k is equal to 1, you can see that whenever there's a single solitary red point present inside the cluster of blues, that whole region turns out to be red, and it makes this blotchy kind of image. So inside the blues region, there's an enclaves of red, which make the prediction not very confident. If we keep on increasing the k, you can see the graph becomes smoother and smoother until it practically divides into two. It becomes a very smooth surface, which means the variance keeps on decreasing as we increase the k in our graph, k in our predictions gradually. And what this means is somewhere inside the range of 1 to 100, 1 to 50, my bad, somewhere inside the range of 1 to 50, there was a perfect combination of k which had the perfect amount of bias and variance in it to form the lowest test accuracy. And to find what that actually number actually is, I've used this piece of code. It takes k all from 1 going till 50. It plots what the testing accuracy of that k value will look like and the training accuracy. We can see when the k is high, the training accuracy is 1, which means the model is perfectly predicting all the training data points. That is, the model is mugging up the answer, which is that it's overfitting. It's not good because it's very much failing at the test accuracy, which is the points that it hasn't seen. So it is not making good predictions with the points that it's not seen. But we can see this red line shows the optimal value. Optimal value being the highest test accuracy. The highest test accuracy for me being the accuracy for the points that the model hasn't seen. So at 11, k is equal to 11, the test accuracy comes out to be almost 0.8, which is the highest, and which means that 11 is where the bias and the variance kind of were in a balance for KNNs. So that'll be it from my side for KNNs. I'll be handing it over to Sekkappan to take it ahead with decision trees.
Yeah, thank you, Shubhansh. Guys, I need you to check if I'm audible. Am I audible?
Yes, you are.
Okay, cool. Yeah, so just give me a second. I'll share my screen. Yeah. Is it visible, guys?
Yes.
Okay, cool. Okay, hi, my name is Sekkappan Vinaithheerthan, and today I'll be taking over for the last part, which is decision trees. And decision trees, as you guess, it is a classification model. It's one of the most popular models out there and the most intuitive models, if you ask me. You don't need any prior knowledge about ML to know about decision trees, because if you think about it, we use decision trees everywhere. Once you get a good understanding about decision trees, you'll understand that subconsciously we use it for everything. So moving on to the contents. First, we'll be seeing what are trees, and then terminologies that are used in trees, and then what are decision trees, an example of decision trees. constructing our own decision trees, and then impurity, Gini impurity, and then an example problem on Gini impurity, and then we'll be going on to the implementation. Now, the very first question, what are trees? Trees is a tree is a data structure that is used in programming. And why do we use data structure? To organize data. And data structures, they have properties. And when you talk about trees, the three main properties that come to our minds are hierarchical structure that they have. They are divided into levels, as you can see. This is level 1, and this is level 2, and this is level 3. And they maintain a parent-child relationship. There is a node over here, and there are two child nodes from the parent node. So basically, if you're in the parent node, you can either go to this child or you can go to this child. And it can be a n-nary tree. Either a parent can have two children, or he or she can have three children. So if it is tree, it's called a ternary node. Moving on, let's talk about the terminologies that we have in trees. First is the root node, the topmost node of a tree, or the node which does not have any parent. Like if you see over here, root is the beginning node. And in a non-empty tree, it should at least contain one root node, which is it should have exactly one root node. And if you think about the root node, it's like the All Father, from where everything begins. And then moving on to branches. Branches is a node with at least one child. It is called a branch. Like you can see over here, this is a branch, it has one child, and this is a branch, it has two child. You can think of branches as connectors. It has both incoming and outgoing edges. Now, leaves. Leaves are the nodes which don't have any child, and it only has incoming edges. There are no outgoing edges. The best way to think about it is the end. It's kind of dramatic, but it signifies the end of a particular path that we have taken in the tree. Like from the root, I can travel over here, and this is the end. Otherwise, I could go to this branch, and then I could go to this leaf, or I could go to this leaf, and I could go to this leaf. So by default, in trees, you will be only able to travel in one direction. There are trees in which you can travel in both directions, but generally decision trees have a single direction. It's unidirectional. And then moving on to the next slide. Yeah, so we have covered terminologies. Next is what are decision trees? So as I said, we use it all the time. It's all about asking a question and then moving on to the next node and asking a question again until you reach the leaf node. Over here, this is the question that you ask, X, Y, Z. And if the answer is yes, you go over here. Again, you ask a question, which is a kind of an action. And you again get the answer. If it's yes, you go to this node. If it's no, you go to this node. So you go on like this until you reach a definitive answer. Like let's say you're trying to find the species of dog. So you ask a series of questions. You only stop when you get an answer. You don't stop midway. So asking the right question matters. So you're trying to find which dog species it is. So you can't really ask, do they have 4 legs? It's not a valid question. It doesn't help you in any way to narrow down the answer. So it's kind of like a detective's job. You have to ask the right question to get the right answer. So what have we learned so far? Trees, what are trees and their properties? The properties include hierarchical structure, parent-child relationship, and n-nary. Terminologies, different part of a tree, like root, the all-father, branch, the connector, leaf, the end. And what are decision trees and how they work? Ask a question, go to the next node. If it's your answer, you're good. If it's not your answer, ask another question. Ask another question until you get the answer. It goes on like this. Next up, we are having an example of decision tree to give you a clear idea of what is decision tree. Over here, I took a simple example of decision tree animal classifier. So we start at the root. We ask the question, is the animal short or is it tall? Let's say the animal is tall. So we go over here. We ask the next question. Does it have a short neck or does it have a long neck? If it has a short neck, we go to this node. Now, does it have a short nose or a long nose? If it has a long nose, it's an elephant. So asking these questions, we found out that our answer is an elephant. And you can see it's written might be an elephant, because this is not an exact decision tree which is perfect. Like, there are many animals which are tall with short neck and long nose. So just to maintain the randomness, they have used might be a squirrel, might be rhinoceros, might be a rat, and stuff like that. So you might go the other way also. So it might be a short animal, and if it can speak, it might be a rat. So this is how a decision tree works. Next. Now let us construct our own decision tree. In this, we are going to use a subset of iris dataset to construct the decision tree. This will be an interactive part where anyone can help me to construct the tree. But I know that only the presenters are allowed to unmute, so it's not a problem. You can just think on your own, come up with the answers, and just verify as I write the answers. So let's start. So let's first talk about the data set. As Naman and Shubhansh emphasized, and I can't emphasize more, knowing the data set is very important. So let's talk about the IRIS dataset, which is one of the most popular beginner-friendly dataset that we use for classification. So it has two main features, sepal and petal. Inside that, you have a subfeature called length, a subfeature called width. Same applies for petal, and your target variable, your response target variable or your end answer is species. And there are three types of species. Iris is the same common name that they have: Setosa, versicolor, and virginica. So to give a better understanding about the features, I have given an image over here. All of the flowers, they have the same color and same texture. The only thing that can be used to differentiate them is the petals length, petals width, and sepal, which looks similar to a petal, but you can see it has a broader end. So this is the length of the sepal and this is the width of the sepal. So moving on. This is a data set that I chose. IRIS dataset has nearly 150 data points if I'm not wrong, but I have chosen only 5 from each category so that it will be easy to follow and construct a decision tree. So the question is, what is the right question that we have to ask? Which feature should we question? Should we question the sepal length that we have? We'll go in order. Let's start with sepal length. Should we ask the question like, is the sepal length greater than 5? We ask the question, is it greater than 5? If it's greater than 5, what is the answer? If it's lesser than 5, what's the answer? If it's greater than 5, it might be virginica or versicolor. If it's less than 5, it might be setosa. But you can see that there is one data point which is 5.1, which is greater than 5. And this is not the only case. You can see a lot of data points that are mixed inside. Like 5.1 is over here, 5.1 is over here. There's 5.6 or 6.2 might be. Yeah, 6.2. And there are many overlaps over here. So you can't get a definitive split over here. You can't say that if it's above this length X, this is this species. If it's below this length, you can't say this is species virginica. So we go to sepal length and we find a similar trend where you have repeated features like 2.5, 2.5, and this is nowhere in 2s. So it might be good to use this, but again the problem is there's 3 over here and there's 3 over here and there's 3 over here. So even if we say if it's greater than or equal to 3, there might be some mixtures, like it might be setosa or it might be versicolor. So we don't want that. Now let's move to petal length. When we come to petal length, you can see there's a clear distinction between the numbers. Like this is in the range of 1.3 to 1.5, whereas this is in the range of 4.1 to 4.3, and this is in the range of 5 to 5.9. Like there is no overlap in the given data set in the petal length. And similarly, if you look at petal width, it also has a clear distinction. There's not much of an overlap also, but the distinction is small. Like the difference between both the numbers is small, whereas over here, the difference between one number and another number is big. So one thing that we can use is petal length, and we can also use the petal width. But let's stick to petal length and construct the decision tree to find out which species the particular flower belongs to. So let's construct a tree. So the first question that we'll be asking is it greater than 1.4? Is it greater than 1.4? If it is greater than 1.4, true. If it's not greater than, which means if it's less than 1.4, false, we go over here. If it's less than 1.4, we know that for a fact that it is setosa. So I'm going to put an S over here. So then we go to versicolor. So we ask the question over here, it's greater than 1.4. We ask them the question again, is it greater than 4.3 also? Yeah, 4.3 is the highest. So we ask it the question, is it greater than 4.3 again? And we have true and false over here. So if it's greater than 4.3, what species does it belong to? It is Virginica. And if it's less than 4.3, then it's versicolor. So you can see over here that we constructed a decision tree ourselves using a sample data set that we have. Now, this decision tree gives you a definitive answer. And as Shubhansh said, there are redundant features in a data set. Like he gave a very good example of the beach and ice creams and sharks, how they seem to be related, but they are not. In a similar fashion, sepal length and sepal width are really not contributing much into this model. So it won't be a problem if we discard these two features. This will make it computationally more efficient, as well as the training time will be faster. So we can just continue with these two features. So there might be some questions that you might have, or at least I asked these questions when I was learning decision trees. How would we find the best feature in a large data set? Like what, say we have 1 million data points and we have like 1,000 or 2,000 features. It's a very large data set. How do we, like manually, we can't just sit and we can't just inspect the data set. We humans, if we are given a small data set, we'll be very good at finding patterns. But if it's a very big data set, it might become trouble for us. So the question 2 is, how will the model choose the feature? Like over here, we manually saw the data set and then we have decided on the numbers and we went on. So how will the model, like how will a mathematical algorithm know which feature to choose? It's kind of interesting. In the next few slides, I'll explain that. What will we do when we have many features, which is similar to question 1, but let's say we only have 15 data points, but we have 1,000 features. At that point, what will we do? It's very similar to question 3. Question 1, my bad. And question 4, what if it is a regression task? As you know, regression is when your target variable is in a continuous fashion. Can regression trees give you a continuous answer? The answer is yes. So over here, when we find out that the petal length is lesser than 1.4, to get the, let's say sepal length was our, let's say sepal, just a second, I know it's kind of messy, let's clear it. Yeah, let's say that petal length is over here and sepal length is over here. Now species is not our target variable, our target variable is sepal length. At that point, what will we do? The best thing is we do the same split, but over here, what we do is when it is lesser than 1.4, we take all the training examples, sepal length, who is lesser than 1.4. We take the average of all these things over here. I think the average will be somewhere around 4.7 only, most probably. So whenever our petal length is less than 1.4, we'll automatically tell the model to output 4.7. Similarly, we take an average of this. So there might be many intervals like this, which might be used for the split. So we take the average of all that and we build on top of it. A regression trees is a session all by itself. So moving on, will this model always work? Like if we always ask questions and questions, don't stop asking, ultimately sometimes we are bound to get answers. So it will always work, yes. Decision trees always work. Like it doesn't work for image processing and other complicated tasks, like for a regular data set which is organized in terms of rows and columns with numerical features, categorical features, and stuff like that. We will have like a structured data. So one terminology that you have to keep in mind is when the data structure is organized in terms of array, a series of arrays, it's called structured data. And when it's kind of an image, or let's say it's audio and stuff like that, it's called unstructured data. So when the data is a structured data, you will always have decision tree working. So the next question will be, if it works for every task, why not use it for every task? That's a very good question. We'll just put a pin on it. In the upcoming slides, I'll answer to that question. So the same tree is over here. We'll just quickly write down 1.4 greater than, this might be 4.3 greater than, and this is Setosa, this is Virginica, and this is versicolor. True, false, true, false. So let me add some technical notations over here. Just notations actually. So at the start we had 15 data points with us. So we'll be writing the 15 as 5, 5, 5. Why is it 5, 5, 5? This 5 indicates Setosa, this 5 indicates Virginica, and this 5 indicates versicolor. And now we go to the next node over here. In this node, what is the split? It's just 5, 0, 0. And the total data point is 5. And the thing is, it is Setosa. And over here, we'll be having 5, 0, 5, and 5. Yeah. So over here, it's Virginica and versicolor. And over here in this node, it'll be 0, 0, 5. And 5 data points are there over here, and 5 data points are over here, and again 5 data points over here. 0, 5, 5. This is Virginica and this is versicolor. So by this array, what do you understand? The initial node, when you try to sample one data point from this node, it has 15 data points in this node. You try to sample one data point from this node, the probability of it being Setosa is 5 by 15, which is 1 by 3. So you don't have a definitive answer over here, which means this node is called impure node. Whereas you go to this node, you sample a data point from this node, and the probability of it being Setosa is 1. The probability of it being versicolor is 0, and Virginica is 0. Whereas you go to this node, it becomes 1 by 2. The probability of it being Virginica is 1 by 2, and versicolor is again 1 by 2. So this node is also impure node. And over here, You see, this is called a pure node because you have a definitive answer over here. When you have a definitive answer, you don't have to split the node further because it's like you got the answer. Why should you ask any further questions? Is the question. Now, moving on. Over here, this, okay, I made a mistake. It's 0 over here. Sorry guys, my bad. So it's 5 and 0, 0, 5. So the probability of, if you pick a data point from this node, the probability of it being versicolor is 1. And the probability of this being virginica is 1. So these two are again pure nodes. So this is the concept of pure and impurity. And why are we discussing about purity and impurity? Because we have to answer the question, how to find the best feature to split in a particular node. And we can't just use impurity because it is a very simple metric to measure for a particular feature that we have. So we come to something called Gini impurity. Let me just change the color. Gini impurity. Gini impurity is a metric by which we find the best feature in the data set for making a split. Like we have thousands of features in a data set. So we find the Gini impurity for all the features at the start, and then the Gini impurity, the feature with the lowest Gini impurity will be the feature that we are going to use for splitting the initial split. And after that, you again get the new node. So again, you will be splitting. Based on Gini impurity again. So this is the formula for Gini impurity. Gini impurity is 1 minus probability of true square minus 1 minus, 1 minus probability of true square minus probability of false square. So the formula, I'll explain the probability part in the next slide. So let's work out an example. You'll understand it better to get a better grasp at it. Let's work out this example. Ignore this index part that you have over here, and let's just concentrate on these three features: weather, temperature, and humidity. So which feature should we split it on? Weather, temp, or humidity? And this is the target variable, play. 0 means not to play, 1 means to play. Given these conditions, you have to find out whether to play or not to play on that particular day. We have 5 data points. So let's start with weather. So we have weather over here. And after getting weather has 3 possible outcomes. One is sunny, one is overcast, and one is rainy. So what we do is, how many data points are there in total over here? 5. And out of 5, we'll use the array index to indicate what target are we currently talking about. Like 0th index signifies 0. So there are 2 not to plays, and first index signifies to play. So there are 3 to play. Totally we have 5 data sets over here. Now we have to restrict ourselves to sunny. When we go to sunny node, we ask the question, is it sunny? If they say yes, we go to this node. So at that point, it narrows down to just 2. You don't have to worry about this because you have discarded. Like you asked a question, so this doesn't come under the consideration. Now you just have this part, this small 2 data points. So inside sunny, we see that there are 2 not to plays, so 2 over here, and 0 to play. So what we do is, what is the probability of true in this particular data set that is there inside the sunny node? Probability of not to play, which is probability of false, is 1 because this is 0. Obviously, whatever you do, whatever you pick, it'll always be probability not to play. So probability of false is 1. So obviously then probability of true is 0. So when you put it in the Gini impurity formula, which is 1 minus this thing square, 1 square minus 0 square, which is 0. So Gini impurity is 0 for this node. So It is obvious because it is a pure split. Like you got a definitive answer that it is, your answer is you are not going to play if it's sunny. So the Gini impurity is 0. Same, if you go to overcast, let me just change the color. If you go to overcast over here, the same thing happens. You have 1 to play and 0 not to play. So at that point, same. Probability of false becomes 0, probability of true becomes 1, which results to the same answer, Gini impurity of 0. And when you see rainy, you might have figured it out. This is also 0 in terms of Gini impurity because of the split 0, 2. So when we take the weather split, automatically you see that everything has a Gini impurity of 0, which means this is the best tree that we can ask for. Like we just asked one single question and we got the right answer. So the question is, how will we calculate the Gini impurity for the feature? We just calculated it for single attributes that the feature has. So if you think of adding these Gini impurities, it's a little bit off, but a good try. The thing is, the number of data points in each node is different, like 2, 1, 2. So you really can't add them directly. And if you're thinking about weighted average, you're right. We have to do an weighted average. So how many data points are there in this particular level? 5. So this will be 2 by 5 into 0 plus 1 by 5 into 0 plus 2 by 5 into 0. So which obviously results into 0 because this is the best split. Gini impurity is 0, which means it's a pure split that we got over here. But what if the split was not pure? Let's talk about temperature now. Instead of weather, we go to temperature. So when we take temperature, I'll just go really quick in this part because I explained how to do the calculation. So same, you just consider hot. When it's hot, the split is 2 not to play and 1 is to play. And when the weather temperature is mild, is 0 not to play and 1 to play. And when it's cold, it is 1 not, 0 not to play and 1 to play. So you know, obviously we have definitive answers. So Gini impurity is 0 over here because when you say the weather is mild, directly your answer is to play. You don't have any other options. But when it comes to hot, you see that even if the weather is hot, you have a 1 by 3 chance of not to play and 2 by 3 chance of, 1 by 3 chance of to play and 2 by 3 chance of not to play. So when you put that in the Gini impurity, which is 1 by 3 square minus 2 by 3 square, whole square, you get some Gini impurity. So this node is impure, which means we have to split it again because we have to reach the end, right? Like you can't just leave at probability, just asking the user to take chances when they have come to you to predict the answer. So again, we go to the next feature. The next feature is humidity. Humidity only has two categories, high and normal. Forget this third line. So right now, you should not examine every one of it. You have to examine just the data points that we have in this node, which is hot, hot, hot over here. So high, normal, high. So if it is normal, we get a definitive answer. That's good, not to play, 0. If it is high, if it's normal, you should not play. Whereas if it's high, you have a chance of 1 and 1, which again makes it impure because it's 1 by 2 and 1 by 2 over here. So it's 1 minus 1 by 2 the whole square minus 1 by 2 the whole square. So again, you have to do the split. Now we come to the weather part again. And in the weather, you should not consider all overcast and sunny. You just have to consider these two parts, the sunny high and the overcast high. Because these are two data points that we are not able to split. So we are only going to question this and this. We are going to leave the rest because we classified them already. So over here, we ask the question if it's sunny or overcast. And when you do that, you get a definitive answer over here for both, because you can see one is to play and one is not to play. So you see, I asked the wrong question. It led to a very big tree. And this is computationally expensive. We can't just play with computational path because it's very expensive. So it is always really necessary to get the right features. Moving on, a quick recap. We saw about trees, we saw about terminologies, we saw about water addition trees, we saw about impurity, we saw about Gini impurity. And now we are going to talk about implementation using scikit-learn. My marker is invisible. My bad. Yeah, scikit-learn. That's cool. Moving on, we are going to do the implementation in Google Colab, and the framework that we are going to use is scikit-learn. Just give me a second. I'll stop sharing and let me share my notebook again. Don't worry guys, I know it's already 12. I'll take just 15 more minutes of your time to explain the notebook. So I'll be sharing this notebook. Is it visible guys? Aman, Shubhansh?
Yes, it is. Yes, it's visible.
Thank you, Shubhansh. Let's go. Let's start. Please don't get scared or terrified by the notebook size. All of this is just for explanation. You don't have to really dive deep into the printing statements, I would say. This is the libraries that I've imported. This is just for making it look good, professional. And a couple of print statements again, like this, which is not required though. I load the data set. We'll just skim through this notebook. We'll just see the outputs because this is to explain the data set, and all of this is just for loop trying to print everything properly. So the features, we are using the same iris data set. As I told, these are the features: sepal length, sepal width, petal length, petal width, and we have 3 classes, and we have used column transformer to convert it to the numbers 0, 1 and 2. And we have used ordinal encoding, as Naman showed at the start, because the flowers are related to each other. Like if it is virginica, there's a close chance that it might also be versicolor. And these are the first 5 rows, and the data statistics. You can see there are 150 data points, and this is the mean, standard deviation, and maximum length of everything. And data visualization. So don't get scared of these graphs. These are not important. The only important row is this one that we have right over here. See, sepal length and target. These markers signify different species that you have. Like the green ones indicate virginica, the yellow ones or the kind of gold ones indicate versicolor, and this is setosa. You can see that we cannot draw a line over here to really split it, like a straight line I'm talking about. You can obviously cut a diagonal line like this, but we are talking about sepal length over here. It's just 1D. You can't really cut because you see there are overlaps over here, and same with sepal width. There are overlaps, like the overlaps are very huge over here. But in petal length, as we found earlier, the overlap over here is perfect, and there is a very little overlap over here. That's why we were able to use decision trees to split right over here. If you imagine, like if you remember, like we did 4.3, it's because of the sample that I took. When you have more sample, it increases. So we'll cut somewhere over here to keep the error minimal. And same, petal width also has some kind of overlap over here. And you can see there is no overlap between setosa and versicolor. So The question is, can we do better than this? And the answer is yes, we can do better than this. As you see, petal width and petal length, when I combine both these features together, you can see there's a very little overlap when considered to this. Like Naman talked about combining features like number of rooms and bedrooms, like average bedrooms in the house, combining both of them by division. Similarly, if we combine both this feature, we find that the overlap is very little. So we can combine these features and give it as a new feature into the decision tree for the classification to get a better model than this normal petal length classification. But the thing is, we stopped at petal length. You can see there is an overlap over here. So the decision tree won't stop at 2 levels. It'll go on further. And this graph over here is illustrating the mean length of each feature, mean of each feature. You can see petal length has it has huge difference between each flower. That's why we are able to easily classify, as well as petal width. Whereas sepal length and sepal width, they don't have that much of a difference in mean. So we trained 4 trees: default tree, shallow tree, pruned tree, and complex tree. So complex tree is where I ask the model to go up to 10 levels. Shallow tree is I ask it to go to 3 levels. Default tree is letting it go until how many other levels it wants. And prune the tree is basically telling the tree not to split a particular node when the sample is 10. Like if it's equal to or lesser than 10, you stop the splitting right over there. Like we had total number of data points in a node, right? Like if it is less than 10, you stop it right over there. You don't go to split even if it's impure. And as you can see, this is the shallow tree that we had. We have 97 accuracy. Over here, as I showed you, the gene impurity is there, the total number of samples, and the array which classifies how many data points like which data point belongs to which class, 35, 35, 35. And over here, see, like Setosa is pure, 3500, gene impurity is 0. But you come over here, it's again 35, 35. You come over here, it's 33, 1. And then we go to gene impurity 0 over here. And over here you see gene impurity is 0.057 and 0.5 after the split. Still, it can go for a further split, but it doesn't. It stops over here because I have restricted the length level to be 3. Whereas in the default tree, it goes on, goes on, goes on. You can see it splits also over here to get the best tree. But why is the accuracy lesser than shallow tree? And if you're guessing the answer is overfitting, you're right. And I'll explain how. And the feature importance, like Naman showed you, coefficient. We also can get a coefficient kind of thing over here. Like a scikit-learn by default gives you coefficients for the feature importance. All you have to do is, you have to just call the model and put feature importance. You get all the important features. And then we have a confusion matrix. Confusion matrix is a way to find out how your model has done. Like actually the flower was Setosa and your model predicted that it is Setosa. Like 15 data points were Setosa and your model predicted them to be Setosa. And 14, you had 15 versicolor with you, and your model predicted 14 of them to be versicolor and it mispredicted 1 to be virginica. And the same for virginica. All virginicas were classified properly. So over here you can see Setosa and virginica were classified properly, so the precision is 1, and 0.94 for virginica because of the 1 misclassification that we did. And recall an F1 score, which is also a measure that we use for measuring how well your model is doing. Precision, recall, and F1 score. F1 score is basically precision by recall, kind of. And then this is a text format of the tree, if you want, but I always prefer the visualization of the tree. And then now we see the last part, which is the decision boundary. Like these were the points that we had in the test data set. And this is how the tree split it. Like right at 2.3 or 4, it's made a decision boundary, which is asking the question yes or no. If it's yes, it's setosa. If it's no, again it asks another question and it finds out which one it belongs to. And then this is basically a graph showing you that as the tree's depth increases, the accuracy becomes constant, both in terms of testing and training. And one thing to notice is we reach very good accuracy for testing at 3, like exactly at 3 if you see over here. After that it drops very much at 4 and 6, 8. So you can plot a graph like this and find out the best model by seeing how close it gets. Sometimes this might not be true because it might just be overfitting on the data set, or there might be a data leak where you have by mistake, you know, put some of your testing data into your training data as well. The split was not proper. And the complexity, like number of leaves increase as the number of levels increase. This is that graph, and this is the observation that we can see. And shallow tree performs the best, and the second most is important feature is petal length. Now let me just stop sharing this notebook, and let me just share the next notebook. The next notebook is really simple, guys. So is it visible?
Yeah, it is.
Thank you, Naman. So as I told you, that was too much in that notebook just because of the visualization. I've boiled down the code to its useful parts so that you can play around with it. These are the necessary libraries that we need for splitting, for loading the data set. We get this, and to plot the tree, and this is the model decision tree classifier, and to split the data set, and to get the accuracy score and classification report, and plotting PLT for plotting the tree, and pandas for organizing the data. So first we load the data, we set x as target, y as target, and x as features, and then we get the feature name and the target names, and then we do x train, y train. Let me just run it side by side. So after that, x train, x test, y train, y test, you do the train test split and stratification y. Now one has explained you what is stratification, trying to maintain the proportions that were there in the test data set. Like if in the test data set, the split between Virginica versicolor and what was it? Virginica versicolor and Setosa, if it's 50, 40 and 10, if the split was like that, we don't want the split to be 50-50 and ignoring one species altogether. Stratification will make sure that the test data set also, represents the training data set, which is 50, 40, 10. The split will be the same. And now we come to the decision tree. Training the decision tree is very simple because of the framework. All you have to do is put decision tree, set a random state so that the tree doesn't change every time you train the model. Right now, let's just remove this max depth thingy over here, and let's just train it. You get this cool curvy box over here, which you can minimize. And yeah, if you want to go for the documentation of decision trees, you can just click on that button over there, and we'll plot the tree. You can see that 1, 2, 3, 4, 5, 6 levels are there, and the gene impurities, everything is visible, and we do the accuracy is 93. And now let's do the max depth thing. I will set the max depth to be 3. So you can see it has added the attribute, and I do the same. See, the depth has become 3. And the accuracy is surprisingly 96. It's better than the last one. Like, we did not get the answers. We stopped at impure nodes over here and here, but still it's performing better. And why is that? Let me go back to my slide. This is the notebook, guys. So don't worry, we'll be sharing this to you. You can go on and see the notebook. And if you want to play with more parameters, like max depth is there, number of leaves can be restricted. You can also dictate the number of splits. Like over here, you can just say that if it's 38, minimum split is 38, it won't go any further than this because it is already at 38. And you can play around with features like that to find out how the accuracy is changing. Let me share my slide real quick. Yeah, coming back to the good old slide. This is the reason why the shallow tree performed better. The tree that we had, the normal tree that we had, it tried to split the data set like this. I think Shubhansh must have also shown you a drawing in which he would have explained how wiggly the line gets when you overfit. Like it's trying to account every data point and it's trying to perform its very best. But the original thing was something like this. When you set the tree to be with max depth tree, this is the point that you get. So when you make the max depth to be tree, you get the optimal function. Whereas when you make it to 10, you basically overfit on the training data. So when the test data comes in, like a new point over here, might be a green point. But your data, because of this decision boundary, it might misclassify that as a star point. That was the reason why shallow tree performed better. And underfitting is basically when I just let it be max depth equal to 1. It'll become something like this. And now coming to the final part, model selection. Model selection is a huge topic by itself. There is too many things that are there in model selection which can't be covered in a single session. So I'll just give you the crux of it. As you are starting with ML, you won't be working with real life data as such. But if you come across real life data, this is how you have to proceed. And I would recommend to start with minimal data sets like MNIST hand digit classification, California housing data set that Naman showed, IRIS data set, and then you have MNIST fashion data set, which can be also used. There are many clean data sets that are available, which needs very minimal pre-processing so that you get the hang of the models first before the pre-processing. So in real life, when you go, understanding your problem and checking your data itself will take you a large amount of time. Like when we do a research, let's say nearly 80% of the time, 80% of the time, you just understand your problem, you check your data, and you do pre-processing. The rest 20% is the fun part where you get to experiment with the models. So there are many problems that you have. Like sometimes your model will be performing good, like it should be performing good, but it is not performing good. It might be because of the data, like you did not pre-process it properly. So all of these problems will be very common. And one thing that you have to remember when you come to ML is it's very similar to coding, like in general, developing and coding and other fields. If you are spending 6 hours in ML to create a model, I'll be very honest, 5 hours will be debugging, finding out what the problem is, and the rest 1 hour will just be the model part that you have. So that is how it works. Now let's just quickly cover this part. Understand your problem. If it's classification, predict category, spam or not spam. Example, classification like clever classification. Regression, predicting numbers like house price that we showed. Clustering, like trying to group similar kind of people. Like in Instagram, you get recommendations. It's because they group you into clusters and then they forward the recommendation throughout that group. And then next you check your data. Is it a small data set or is it large data set? Like Shubhansh told you, KNN is not suitable for a large data set. If it's a small data set, go for KNN. If it's a large data set, go for linear regression. If it's a small data set, I'll say go for decision trees again. And one more thing, I forgot to answer the question, why not use decision tree for all structured data? The thing is, as I showed you, decision tree is capable of finding the answer no matter what. So it'll obviously overfit for all the problems that you give, which are not even meant for decision trees. So it's always better to not use decision trees. And that's when advanced models like XGBoost, CatBoost, Gradient Boost, Random Forest, and other models which are based on decision trees, like a group of decision trees combining together to find the answer. And then you see if it's labeled or unlabeled. If it's labeled, you go for supervised, unlabeled, unsupervised, and then you go to the fun part. Start simple, go for quick and dirty implementation like logistic regression and decision trees, linear regression, and random forest regression. If it's clustering, go for k-means. Go for small models, easy models, check out how they behave before going to complicated models. And if you feel like the small model has reached its saturation point, then you need to scale up. And to scale up, you go for neural networks, transformers, CNNs, and random forest, gradient boosting, XG boosting for better accuracy. This is how you do it. And then that's it, guys. Thank you for joining this session. In the next session, we'll be teaching you about neural networks and their propagation techniques. We'll be explaining and emphasizing more on the mathematical part so that you get an intuition of what is neural network and how it is derived from neural linear regression, and how to implement linear regression and neural network from scratch. Like over here, we used scikit-learn library to show you how everything is done. We'll be showing you how to implement it from scratch using functions and NumPy and pandas to do it. So that's about it. Thank you guys for joining.